which is a biology seminar about blight on chestnut trees. And then the one on Thursday is a chemistry seminar about, it's a person who, she's a Berry graduate, and she currently works for Procter & Gamble in their analytical labs. So it's interesting, like, what do chemists do? She does the industrial side of chemistry, which is kind of neat to think about. So. All right, so let's do some ice charts. Yay, ice charts. All right, so let's say this is the more likely scenario. All right, we have the equilibrium constant. We'll have Ka. And we have some information about pH, or initial concentrations. Like, this is the more likely experimental scenario. So let's say I have a weak acid, and I know its initial concentration, and I know its acid equilibrium. I would like to know what the equilibrium concentrations are of all the species once the reaction has reached equilibrium. So what do we always do when we go to start these kinds of problems? First step, I need to do something first. I need to write out a balanced equation. And so I have a weak acid. Does it say what the weak acid is reacting with? So what is it? What do we assume? Right? We assume water. So if I have a weak acid reacting with water, what must be one of the products I'm going to make? Right, I'm going to make some hydroniums. And then I just have A minus left. All right, so now we're ready to set up our ice chart. So what's my initial concentration of HA in this problem? All right, 0.04. Do I initially have any of my products? No, I don't initially have any of those. All right, so we can fill in our ice chart. All right, so far so good. So then I could write out my equilibrium. Right, that's all true based on all the stuff we've done like a million times now. If I wanted to solve this, how would I go about solving it? We're not going to solve it right now. We're going to think through it. What do I need to do in order to be able to solve this? Right, I got a quadratic equation going on. How many people love quadratics? 2. How many people are like, well, I wish there was a way around this? We're going to do a way around it. So you are more than welcome to do a quadratic every single time, but I'm going to show everybody a shortcut of how to not have to do a quadratic every time. So let's think through this. Right, I have a weak acid with a Ka of 4 times 10 to the negative 9th. How likely is it that I'm going to make a lot of these products? Not very likely, right? Weak acids don't dissociate completely, right? That's the point of being a weak acid, so I shouldn't make very much of this. If I don't make very much products, how big is this X? It's going to be tiny, right? How tiny is it? So tiny, it is negligible. We can not use it. So, we'll write all that out in case you forget later. All right, so because HA is a weak acid, it does not ionize completely. Ionize. So we can say X is small, so I can actually say this is really 0.040. So that should make our math a lot simpler. So now I have look how much nicer that is. All right, so let's go ahead and solve that. Everybody get something like that? Make sure my math is good today. Mm-hmm. Yep, molar. Yep. Let's square root that. Good. All right. So once we get to this point, we have to ask ourselves, how good was that approximation? All right, so experimentally, we know Ka values to plus or minus 5%. We know them pretty well, right? But there's a little wiggle room in how well we can measure them. So this means if our value of x is less than or equal to that 5%, then we have made a good approximation. So what we need to do is check our x value to see if it's 5% of what our original value is. So the question is this value less than or equal to 5% of that? So we can do it one or two different ways. You can figure out what 5% of this is and see if this value is smaller, or you can take this, divide by that, times 100, and figure out what percentage it is. I think that's easier. I think it's easier to do it this way. It's sneezing here today. Let's see, I get this to be that. Is that less than or equal to 5%? I'll wait for everyone to catch up. Apparently everyone's calculating. Seriously thinking about it. It is definitely less than 5%. Yes, good, just checking. Whew. So, did I make a good approximation by assuming x is small? Yes, I made a good approximation. So, now that I know that this is a good x, we can finish solving the problem. So, what was x in my original ice chart? All right, my H3O plus. And so, I found this is that. So, I can say HA is still 0.04 molar. A minus is equal to H3O plus, which is equal to 1.3 times 10 to the negative fifth. So what is going to be my follow-up question if I know the hydronium concentration? What is the pH? So how do I figure out pH from the hydroniums? Mm-hmm. So what would we expect this pH to be? 7, less than 7, more than 7. Should be less than 7, right? Because I put a weak acid in, and the only thing I'm making is more acid. So it should be less than 7. So as you're calculating, double check, you get something less than 7. 1.3. pH 4.9. Does that match up with our expectations? Good.
How did you set the A minus equal to H3O plus?
Because they're both X.
Oh.
Yep. How do I feel about that? Good? Let's do another one then. My plan is just to do 3 really good practice problems. All right, so let's see here. Oh, this is my 3rd practice problem. We'll come to that. Let's do another warm-up before we get to the challenging one. All right, so this is more likely what the problem's just going to say. It's going to say very little. It's going to say find the pH of a 0.1 molar ammonia solution. But we're going to use the same steps we've used a bunch of times before. First question, is ammonia a strong acid or a strong base? No. Is it one of our weak acids or is it a weak base? It's a weak base. So if it's a weak base, and it's a solution, so it's doing this. If it's a weak base, what do we expect one of the products to be? Yeah, we need to make some OH minus. Then we should have some NH4 plus. Good. Good, good. We should get, you should be at this point fairly speedy at being able to write these kinds of problems. All right, so then we are ready to make our ice chart. All right, we fill in the information we know. Okay, if I have a weak base as my reactant, do I use an equilibrium constant that refers to an acid or an equilibrium constant that refers to a base? Refers to a base. So I need to use the Kb for this. So that is often the thing that trips people up. If you're starting off with a base, you got to use a Kb. Starting off with an acid, you use the Ka. So when you're reading through your tables, make sure you pick the right combination of Kas and Kbs. So, all right, so I would look this up on the table and I'd see it's 1.76 times 10 to the negative fifth. All right, so NH3 we just said is a weak base. So what assumption can I make about the denominator for this problem? Right, I'm just going to assume the X is very small. And then I'm left with this. All right, so calculate along with me, make sure I did this right. 1.76, negative 5 times 1. All right, so now I have an X value. We need to check if it's truly 5%. Right, did I make a good assumption? Any guesses on my assumption? If I was guessing, I would guess it's a good assumption because I'm in the section where I'm making good assumptions. So, can I move forward with the X being small?
Yes.
Yes, because it is less than 5%. Cody?
Yeah, but over 5%, you're going to have to automatically do the quadratic.
I'm going to say it is unlikely I'll have you do a quadratic on the exam, only because they are time-consuming to set up. But you'll need to make sure that I'm not trying to trick you. I don't think I'm going to try and trick you. If we have a problem that has a quadratic, I will explicitly state either it needs quadratic or stop after setting up the quadratic. Because the hardest part is setting it up, and then solving it takes forever. So, since we only have an hour to take a test, I can't have you spending 45 minutes plugging it into your calculator. So, our 5% rule, it'll be pretty obvious on the test one way or the other. So, all right, so now what is my next step? Right, I want pH. Can I get to pH from right where I'm at right now? Right, so when you get your quizzes back at the end of class, pH is this. Is that a lot of people swapped partners in this thing. So I gave you on the quiz an OH concentration, which means you can find a POH. You can't go from OH concentration right to pH. So just figuring out which one do you have and then subtracting the other one from 14. All right, so I have this, which means I have the OH concentration. All right, so what does that turn out to be? What would we expect the pH to be? Above 7, below 7? Right, we expect it to be above 7 because it's basic. True. All right, how do I feel about those so far? Ready for the challenge problem? Codeine is a powerful and addictive painkiller that also happens to be a weak base. So we have a few parts to this problem. I want us to be able to write out the equation of the weak base codeine reacting with water and predict the products. If I know the acid equilibrium constant of the acid form of codeine, how would I figure out the base equilibrium constant? And then we'll actually figure out the pH of a solution of codeine. So, all right, so if codeine is a weak base and it's reacting with water, how is water acting? Right, it's acting as the acid. So what should one of our products be for this? Right, we have to make some OH minus. And if water has become OH minus, what is my other guy? Right, HCOD. Good. Okay. I'm going to do part 2 right here. It doesn't. As long as you keep track of which one's which. All right, if I know the acid equilibrium constant, how do I find the base equilibrium constant? How are they related? Through Kw. So Kw, Ka times Kb. If it was pKs, then they had to be pluses. Okay, what is the exponent on the Kw? We know for sure it's this. Negative 14.
What is negative 7?
That is hydroniums and hydroxides in water, like neutral plain water. So the Kw comes from the fact that the concentration of hydroxide and concentration of hydroniums times each other are each minus 7.
Okay.
All right, so then we can find out Kb. Everybody get something in the ballpark of 8.3 to the negative 7th. For those playing along out in the audience. Okay. All right, so now we're ready to do an ice chart. All right, so in the problem, I said I have a 2 times 10 to the negative 3rd molar of solution of the codeine. All right, that's water. We don't have any of those. Eventually, I'll give us a problem where the x's aren't just 1. But one thing at a time. All right, so now we're going to set up our KB, which we just solved to be 8.3. Okay, so this is a weak base. What assumption can I make about this x over here? All right, small, so I'm just going to leave it off. So let's figure out what x is. I did not do something right. Let's see, 8.3, -7. No, that makes more sense. All right, so now I have x. How do I check to see if it's less than 5%? Yep. Yep. Can I make this assumption? Did I make a good assumption? Okay. So now I want to find pH. What do I have anything to help me find pH right now?
Yeah, you have the OH.
Right? X is telling me OH minus. So I can figure out the POH. So now I can figure out the pH. Does that pH seem reasonable considering we're starting off with a weak base? It does. We made a basic pH. So that should check off in your head like, oh, good. All right, how do we feel about those? Good, confident. All right. In that case, what I'll do for the rest of class period